So hello, good morning, everybody. Thank you very much for being here in this new Severo Ochoa colloquium. Thank you for being here, and overall, thank you for having accepted our invitation, Dr. Antonino Francesco Lanza. He graduated from the University of Catania in 1989, and then earned his PhD from the University of Catania also in 1993. He is an astronomer of the Italian National Institute for Astrophysics, INAF, and his current main field of study is the interaction between extrasolar planets and their host stars. He's also interested in the sun as a star, and also in the physical processes related to the rotation and magnetic fields in late-type stars, both single and in closed binary systems. He's one of the founders of the GAPS collaboration, GAPS coming from Global Architecture of Planetary Systems, which is aimed at discovering new planetary systems and investigating their properties and their evolution. He collaborated in the space mission Corot for Spanish people, as a guest investigator, and is involved in Gaia as a member of the CU7 variability processing. He's presently working on the science management of which you all know is recently approved this mission to discover exoplanets and study their evolution with the most advanced methods of astrophysics. Today, he's talking about the stars and their close by planets, clues of magnetic interactions. And so I insist on thanking you, Dr. Antonino Francesco Lanza, for having accepted our invitation. And the floor is yours.
Thanks a lot for your nice introduction. Thanks to you for coming. And thanks to Miguel and Pedro for their kind invitation made possible by the Severo Ochoa program. So for me, it's really an honor and a great pleasure to be here and to spend this, 40 minutes just speaking about star-planet interactions and possibilities to observe them. Stars interact with their planets through the gravity field, which is producing tidal effects. The radiation field, in particular, the extreme ultraviolet, is important because it produces evaporation of young planets. And also, magnetic fields of the star and of the planets interact, and stellar winds are crucial to that kind of interaction. Today I will focus on magnetic interactions. Magnetic fields play an important role for exoplanets. We can learn from the solar system that magnetic fields are crucial to reduce the evaporation due to the stellar radiation. And in planets that are very close to the star, this effect is probably much more important than in the solar system. They can also protect the planets from the impact of coronal mass ejection and affect the habitability of the planets themselves. Moreover, from the astrophysical point of view, magnetic fields provide information on the planetary interior because a dynamo requires the presence of a fluid layer somewhere inside the planet. I will not discuss the impact of magnetic fields on exoplanet habitability. You may find information in the review by Ira Petian et al. 2019. I will discuss some hints of star-planet interaction that comes from observations, and I will focus on the effects that we observe on the star, because planets are impossible at the moment to detect directly, except in a very few cases. So what we can hope to do is to observe effects of the star-planet magnetic interaction in the star, in the host star. In the solar system, planets are located in a region where the velocity of the solar wind is larger than the local Alfven velocity. The Alfven velocity is defined as the ratio between the magnetic field and the square root of the magnetic permeability times the density of the plasma. In the solar system, the solar wind is fast in the sense that its velocity when it reaches, for instance, the boundary of the Earth magnetosphere is larger than the Alfven velocity. And in this case, you form a bow shock at the boundary between the magnetosphere and the stellar wind. In the case of planets that are very close to their stars, which is actually the majority of planets that we know today, you are in a different regime because the stellar wind is accelerated in a progressive way as you move away from the star. So when you are very close to the star, the regime is probably sub-Alfvenic in the sense that the velocity of the wind is smaller than the Alfven velocity. In this regime, the perturbation produced by the orbital motion of the planet on the magnetic field lines can move back to the star. In the solar system, this is not possible because any magnetic perturbation produced by the motion of the planet is blown away by the solar wind, and so it cannot reach the sun or in general the star. A perturbation produced by an orbiting planet moves along characteristic lines. Characteristic lines are the lines that at each point have as a tangent vector this CA, that is the sum of the difference between the plasma velocity due to the wind, which is V, and the vector Alfven velocity, VA, that is along the local magnetic field. There are two characteristics. One is usually pointing towards the star when you are in a subalbenic regime, while the other is pointing away from the star. And energy, due to the perturbation induced by the planet, are propagating along those characteristic lines. So in a subalbenic regime, the perturbation, at least those moving along the inner characteristics, can reach the star. In the solar system, we have an interesting analogy in the Jupiter Io system. Jupiter aurora can be seen here, observed in ultraviolet using the HST telescope, and in the auroral oval you see some bright spots. The most prominent one is this one, and it moves in phase with the orbit of Io, the inner Galilean satellite of Jupiter. There are also spots associated with Europa and Ganymede that are at larger distances than Io. You can see here the ratio between the semi-major axis of the satellite's orbit and the Jupiter axis that goes up to 15 in the case of Ganymede. Io has no intrinsic magnetic field, and Europa probably is the same. Only Ganymede has a field that is really very small, much smaller than that of Jupiter. In the case of the bright spot produced by Io, what we know since now 40 years is that the motion of Io inside the magnetosphere of Jupiter continuously excites Alfven waves, produces a continuous flow of perturbations that move along the magnetic field line and reach the polar region of Jupiter. The perturbation propagates as an Alfven wave, and those waves are dissipated in the denser layers of the Jupiter atmosphere, producing this bright spot. In addition to the phenomena that we see in the ultraviolet, we also see a coherent radio emission that peaks around 40 megahertz and is best observed close to the quadratures when Io and Jupiter are in quadrature with respect to the Earth observer. The brightness temperature of that emission is extremely high, which means it is produced by a non-thermal process. The emission is highly circularly polarized, it's beamed and relatively broadband. All these characteristics are typical of a coherent mechanism. In this case, the mechanism is the electron cyclotron maser, and the peak emission of that maser is at 2.88 times B megahertz, where B is the magnetic field in Gauss. In the case of Jupiter, with a field in the polar region of 14 Gauss, this means that the peak is around 40 megahertz. The emission is produced close to the foot point of the field lines that connect Io with Jupiter. So it's produced closer to the bright spot that we see in the ultraviolet. To have a maser, you need a non-equilibrium distribution of the population of the electrons. Here, the distribution of the momenta is no longer isotropic because the electrons having a velocity that is almost parallel to the field lines can go deep into the atmosphere of Jupiter and are lost. The electrons having some component of the velocity that is perpendicular to the field line are reflected in the close to the foot point of the magnetic field flux tube of Jupiter, and they actually contribute to the non-equilibrium distribution that produces the emission. The emission is not isotropic, but the maser radiation is emitted over the surface of a cone, and so we see it when our line of sight intercepts the surface of the radiation cone. The mechanism that provides energy to the electrons responsible for the emission are the Alfven wings. Alfven wings are these Alfven waves that are excited by the motion of Io inside the magnetosphere of Jupiter. Io is a conductor because it has a ionized layer close to its surface. It has no intrinsic magnetic field, so basically the ratio of the obstacle is almost coincident with the ratio of the satellite. And moving across the field like a boat over the surface of the sea, it continuously excites Alfven waves, and those waves then propagate away and they move along characteristics. And the inner characteristics, in the case of Jupiter, points towards its poles. Here you can see a scheme illustrating what happens in the case of a body with an intrinsic magnetic moment, a planet with a magnetic moment, MXO. In this case, the size of the obstacle is larger and corresponds to the boundary of the magnetosphere in the stellar wind. There are several angles here that are important, especially the angle between the magnetic field vector, the velocity of the wind, and the orbital velocity of the body. The theory can be found in the work by Joachim Sauer and collaborator, especially in the paper they published in 2013, and the review is in the Handbook of Exoplanet. This is the paper I used to find this picture. The Alfven waves propagate along characteristics. Here, one characteristic, Ca plus, is pointing away from the star. The other one is pointing towards the star, and this Ca minus. In the far field, the waves are still moving in a coherent way. They do not, there is no dispersion of the wave because Alfven waves are transverse waves that move along magnetic field lines. So they are, in some sense, keep close to the field lines and can reach the star. Magnetosonic waves, like fast waves or slow waves, on the other hand, they have a more isotropic propagation, and so their flux becomes smaller and smaller as we move away from the source of the perturbation, that is the planet. In the case of stars, we can monitor the heating in the chromosphere using the flux in the core of resonance lines, in particular the calcium 2 H and K lines. Those lines show a reversal in their core, and this reversal is due to the heating of the chromosphere. It has an acoustic component that is independent of the magnetic activity, but it also has a component that depends on the non-radiative heating of the chromosphere produced by the dissipation of magnetic energy. In solar-like star, we can derive an index called the S-index, which is a measure of the flux in this reversal in the core of the lines. And this is a good way to monitor the chromospheric emission in those stars. There are a few systems that have hot Jupiters and that show some hint of star-planet interaction. The amplitude of the effect, as measured by the S-index, is small, is of the order of 1–2% in the best cases. So this requires dedicated observations. You must observe at least for 2 or 3 hours in a night to reach a precision of the order of 0.5% in the measurement of the S-index, even if your star is bright. And you also need to extend those observations to cover the orbital period of the planet, but also the rotation period of the star, because the S-index is modulated by stellar rotation in late-type stars. And if you want to disentangle the modulation given to the stellar rotation from that produced by the star-planet interaction, you need to cover both the relevant periods, the rotation period as well as the orbital period. And the rotation period can be long. So it's really, difficult to make these observations because in addition to the long sequence that you have to obtain in each night, you also need to extend the observations, usually for a couple of weeks, in a continuous way, and that requires actually time. Observing time is not easy to obtain on medium or large size telescopes. In addition to that, there is the problem that the signal of star-planet interaction is non-stationary. We observe it usually in 50–60% of the season, even in the best target. And for this reason, we must say that no target has currently a fully significant detection that is at the level of 3 or 4 sigma. However, taking all the proposed detection as an ensemble, I would say that we have indication that magnetic star-planet interaction is actually happening, at least in some seasons and in some weeks. The best candidate is HD 179949. It's an F-type star having a rotation period of about 10 days at the equator, and it hosts a hot Jupiter with a period of 3.1 days. Here on the left, you see the chromospheric S-index put in phase with the orbit of the planet. During some seasons, you have this peak of emission around phase 0.7, 0.8. that is actually with an amplitude of 2.5%. It is observed in about 60% of the seasons. Another targets that show a detection is HD 189733. This is a K-type star with a hot Jupiter on a short period orbit of 2.2 days. In that case, the probability of a false alarm signal has been estimated, and it's of the order of 1%. The same false alarm probability applies also to the case of HD 179949. The four systems with the best detections are shown here. On the top line, you see the residual profiles in the core of the K line that is obtained by subtracting the average profile from the single night average of the K lines in this star. In the second row, you see the estimated power emitted in the core of the K line versus time. And on the third power, you see that in phase with the rotation of the star, and in the lower row, you see that in phase with the orbit of the planet. So the first column is for HD 179949, and you see that the signal is much better reproduced when you put in phase with the orbit of the planet than when you consider stellar rotation, at least in that season. For HD 189733, you first have to remove the intrinsic rotational modulation that is indicated here by this blue line. And after removing the rotational modulation, you can see some signal in phase with the planet in the residuals. Tau Boo is the third candidate, but in this case, the rotation of the star is almost synchronous with the rotation of the planet. So we must admit that in this case, we don't know whether the modulation is due to rotation, so it's intrinsic, or it's due to the planet. And the final one is Upsilon Andromeda. Coley et al. In 2019 used the observations of those four systems to estimate the maximum power that is emitted in the calcium K line and found values of the order of 10 to the 20 watts. Going to the X-ray observations, HD 179949 has been studied by Acceria and collaborators, and this is the periodogram of the X-ray flux. It shows a signal that is significant, slightly above 2 sigma here at the planetary orbital period. This is the planetary orbital period, and this is the signal just going a little bit above 2 sigma. Other power going above 2 sigma is here, close to the bit period, the synodic period, between the polar rotation rate of the star, that is 7.6 days, and the orbital period of 3.1 days. Another example of star-planet interaction is in AUMIC, that is a pre-main sequence star, very active. Klein et al. Found a significant periodicity close to the orbital period of the inner transiting planet in the helium-1 D3 line, and a signal with the lower significance in the sodium-1 D1 and D2 lines. If we include the signal produced by flares, the FAP, the false alarm probability, is 0.2% in the modulation of the helium-1 D3 line. Here, the X power is of the order of 10 to the 17 watts. And then I come to radio emission. There are three stars that are interesting for our purposes. The first one is GJ1151, which is an inactive red dwarf. Then we have Proxima Centauri and YZ Ceti. Proxima and YZ Ceti have close by planets that have been detected with the radial velocity monitoring. GJ1151 has no close by planet. It actually has a planet, but it's a planet far from the star, at least 0.57 AU from the star. So we think this planet is not able to produce a significant interaction. Probably if the signal is associated with a planet in this star, there is another body, but presently we have only an upper limit for its mass. The upper limit is 1 Earth mass for periods between 1 and 5 days. So the search for this hypothetical planet is going on, but at the moment the best candidates are Proxima and YZ Ceti. The first one, GJ1151, showed the emission in a low frequency between 120 and 167 megahertz. Whereas the other two candidates, Proxima and YZ Ceti, were detected at a frequency around 1.5 gigahertz, so a significantly higher frequency. In both, in all the three candidates, the emission is episodical and has all the characteristic of the electron cyclotron maser emission, the same mechanism that we see at work in Jupiter and Io system. And the temperature of brightness, again, is very high in this coherent mechanism of emission. If we use the formula that connect the magnetic field with the frequency of the peak emission, we need a field of the order of several tenths of Gauss in the case of GJ1151, but we need a field of the order of hundreds of Gauss in the case of Proxima and YZ Ceti. So in those two targets, we think the emission is coming from the foot point in the stellar corona, close to the star. It's not emission in the planetary magnetic field, as in the case of Jupiter, but it's emission in a magnetic field in the stellar corona, because the intensity is close to the field strength we measure in M dwarfs using spectropolarimetry or other techniques that give us information on the photospheric field. The interesting point about Proxima is that it hosts 3 planets. Here we focus on planet B, that is an Earth mass planet with a period of 11.2 days. There is another planet with a period of 5 days, but its mass is very small, is only 1/4 the mass of the Earth, more or less that of Mars. So this body probably is not able to produce a strong interaction with the stellar field. The planet orbiting with a period of 11.2 days is actually an Earth-sized planet, or a little bit more massive than the Earth, so it's the best candidate for the interaction. The third planet is very far. It's a period of 5.2 years, so we don't think it can interact significantly. The radio emission of this star has been observed at 1.62 gigahertz by Miguel and his team, and they found that the emission is stronger at the quadrature, which is reminiscent of what we see in the Jupiter Io system. And this also is reinforced by the emission observed during flares in Proxima. So it's an indication that together with the electron cyclotron maser mechanism at the base of the mission, that we are observing something that is similar to the Jupiter Io phenomenon, but here it is between a star, an M dwarf, and its close by planet. The intensity of the field responsible for the emission is of the order of 600 Gauss, which is in general agreement with the field that have been measured using spectropolarimetric techniques in Proxima. So just to summarize those observations, we can say that the chromospheric hotspots emit powers of the order of 10 to the 20 watts, while in the radio, the emission from Proxima amounts to a power of the order of 5 times 10 to the 14 watts. So it's much smaller. Radio techniques have a much higher sensitivity. And more or less the same order of magnitude is applicable also to GJ 1151. But in that case, as far as we know, at the moment, no close by planet has been found. So the next question now is, what could be the physical mechanism responsible for releasing those power levels? Well, we have several candidates. The first one is the Alfven wing model, and it is based on what we know from Jupiter Io system. Saur and collaborators have published this paper in 2013, where they developed the theory of the Alfven wings for stars with close by planets. Using a specific model of a stellar wind, they found that close close planets within 0.1 AU are in the subalvenic region of the circumstellar space, and in this case, Alfven waves can move back to the star. They can produce effects in the star. Here you see with different symbols that refer to the spectral type of the host star, all the planets that were known at the time they published their paper. You see in the right panel the power level that is produced by the Alfven wings, the pointing flux close to the star. And the level of power is at most of the order of 10 to the 19 watts in the best cases, but usually it is lower by 1 or 2 orders of magnitude. So this mechanism does not appear capable to account for 10 to the 20 watts, the power radiated by the chromospheric hotspots. This mechanism has also been studied numerically. And in particular, Antoine Strugarek has made several models for this interaction mechanism, considering planets that have no intrinsic magnetic field, which is the unipolar model, or planets having an intrinsic field, which is the dipolar model. Depending on the conductivity of the planet atmosphere and the planetary interior, in the unipolar model, you may have different kind of interactions, but in any case, you excite Alfven waves and then move along characteristics. What changes is the degree of penetration and the degree of dragging by the planet of the stellar field line. More interesting is the case of a planet with an intrinsic magnetic field, because in this case, when the field lines of the planet and those of the stellar wind are aligned, you get the maximum effective area of interaction. And in this case, you can get the maximum power, of course, again, of the order of that predicted by the analytical models. But it's interesting to note the difference with the case of a planet with an anti-aligned field. Since the stellar wind has a field with a changing polarity, because stars like the sun and late type stars in general have magnetic cycles, and during those cycles you may have a reversal of the stellar field, you may go from the aligned to the anti-aligned configuration. along the stellar cycle. And in that case, on the right, you see that when you change the configuration from aligned to anti-aligned, you get a reduction of the available power by more than 1 order of magnitude. So this can explain the lack of signal that we see in about 50%, 40-50% of the seasons. Another model that has been proposed is the unipolar inductor model. It assumes that the planet moves inside a dipolar stellar field. Originally, the model was proposed for T Tauri stars that have strong, large-scale dipolar fields. The planet is a conductor, has no intrinsic field, and when it moves crossing the field lines of the stellar dipole, it induced an electromotive force. You see here with this vector VPS, the velocity, the orbital velocity of the planet, of the conductor. It is going inside the plane of the screen. The field at the equator of the star is directed vertically, so the field induced by the motion of the planet, which is along V cross B, is directed along the radial direction towards the star in this case. These fields can produce an electric current that moves along a circuit. In the northern hemisphere, we have a circuit including the planet with the electric resistance Rp, and then the current flows along the field lines and goes into the stellar atmosphere. In the stellar atmosphere, you may have a dissipation if the electric resistance is high enough. Actually, this model is valid if the Alfven waves can move back and forth on a time interval that is shorter than the time taken by the field lines to slip across the diameter of the planet, which means this model can actually be applied only if the period of the planet is short, of the order of 3-4 days at most. It has also been simulated numerically by Antoine Strugarek in several of his work. The unipolar inductor can be applied not only to T Tauri stars, but also to late-type stars. If you assume a dipolar global field of the star of 20 Gauss at the pole, you get the right amount of power, 10 to the 21, 10 to the 22 watts, the amount needed to explain the chromospheric hotspot. However, the problem with this model is that it is limited to very close by planets, and also there are several unknowns, in particular the depth where the electric currents flows inside the stellar atmosphere, and that depth is crucial to find the value of the electric resistance of the star that produces the dissipation. So in principle, even if this model is capable to produce enough power, there are many unknowns, and this means that it's worth exploring other models. Another simple class of model simply extend the hypothesis that we use when we describe the solar corona to larger distances. They assume that the gravity and the plasma pressure are negligible in comparison to the Lorentz force. The plasma velocity is much smaller than the Alfven velocity, and also they assume that the system is stationary. All these hypotheses give force-free fields, which is a very good approximation for the inner solar corona, but actually it's only a very rough approximation for the outer corona, where close by hot Jupiters are located. But let me a little bit explain what we can learn from those models. Well, in MHD, the electric current density is simply proportional to the curl of the magnetic field. The Lorentz force is given by the cross product between the current density and the magnetic field. A force-free field means a field where the Lorentz force is close to zero. So the electric current is basically given by this equation. It is directed along the magnetic field. Alpha is a simple scalar, and if you take the divergence of both sides of this equation, you have that alpha must be constant along magnetic field lines. When the field is potential, alpha is zero. So a magnetic field with the potential field lines is characterized by alpha equal to zero along those lines. If alpha is different from zero, you have a current and the field is non-potential. So this kind of approach tells us that there are two different possible configurations. The first configuration is characterized by field lines that interconnect the star with the planet. Since the field in the planetary atmosphere and close to the planetary surface is potential, alpha is zero close to the planet, and must remain zero all along the interconnecting field lines. So this kind of interconnecting configuration is possible, but only if the stellar field is potential. At least some part of the field, some of its field lines must be potential. Otherwise, you cannot have a stationary configuration. If the field of the star has no potential field lines, then the two system of field lines, that of the star and that of the planet, are topologically separated. Where there is a region where the two systems of field lines come into contact, and in that region you may have a magnetic reconnection, but you cannot establish a permanent magnetic connection between the planet and the star, at least in this simple model, because after reconnecting, they soon disconnect because alpha must be constant along a given field line. So we can compute the power available in those two cases, in the cases of those two general configurations. In the case of magnetic reconnection, the power depends on the field of the star at the distance a of the planet on the equatorial plane. It is assumed that the orbit is on the equatorial plane. It depends on the angle between the field lines of the stellar corona or the stellar wind and those of the planet. And this is parameterized by gamma. Gamma goes from 0 to 1, and it's 0 when the field lines are parallel, so there is a minimal or no reconnection, but it becomes 1 when the field lines are directed in opposite direction. Rm is the radius of the planetary magnetosphere that can be estimated by assuming that at the boundary of the magnetosphere you have more or less equality between the magnetic pressure of the stellar coronal field and the magnetic pressure of the stellar planetary field. With this model, the interaction occurs between weak fields because it's the field of the star but at the distance of the planet. For a dipole field, which means that the intensity of the interacting fields is of the order of 10 to the minus 2 Gauss, even if at the pole of the star the field is of the order of 10 or 20 Gauss. So the available power is very small, is of the order of 10 to the 17, 10 to the 19 watt. And this is similar to the maximum power that we get in the case of the Alfven wing model. On the other hand, in the interconnecting loop model, the situation is different. In this case, you have a loop interconnecting the star with the planet, and you apply a stress at the foot point due to the orbital motion of the planet. Now, the field that is relevant is the field at the pole of the planet that can be of the order of 1 or 10 Gauss. If I assume a field of 10 Gauss, like in Jupiter, and the typical orbital velocity of hot Jupiter, I get a power of the order of 10 to the 20, 10 to the 21 watts. Actually, in this approach, as soon as I stress the field, I inject energy into the magnetic field, and the field cannot remain potential unless there is some very efficient dissipation. What I am assuming is actually this regime in which as soon as I inject the power into the magnetic field of the interconnecting loop, that power is immediately dissipated inside the same loop, and this mechanism with very efficient dissipation can keep the field close to the potential configuration and keep the connection between the stellar coronal field and the planetary field. So this model is promising if actually it occurs in reality, and it has been applied by Cowley and collaborators to estimate the magnetic field strength at the planet in the case of the 4 hot Jupiters that I showed you. They assumed that a fraction E of the total energy that is delivered by the process can be radiated in the K line of the ionized calcium. That fraction is small, is taken from a solar flare observation, is of the order of 0.1, 0.2%. The stellar fields in this case are not relevant, but actually they have been measured. And from the application of the formula that gives the power and the assumed efficiency, we get field strength between 20 and 120 Gauss. Those fields are shown here in this plot on the y-axis versus the field that is predicted by the model by Yadav and Thorngren, who assumed that some of the stellar radiation is reprocessed inside the hot Jupiter and contribute both to the inflation of the radius that we observe in most of the hot Jupiters, as well as to the increasing in the efficiency of the convection and then of the dynamo. So the idea by these two authors is that we can interpret both the inflation of the planetary radius by the insolation, by the installation of the star, and also stronger fields are predicted by this model used to interpret the inflation of the radius, and those fields are close to the values that actually, at least for those 3 planets here, close to the values that are predicted by the interconnecting loop model. The only exception is Tau Bu, but Tau Bu is a system with a synchronized planet, so it cannot be actually compared with the other 3 stars that are not synchronized to the orbit of the planet. The interconnecting loop model is based on many approximations, in particular approximations that are valid in the inner stellar corona, but not probably in the outer corona. So it's good also to compare with the results from numerical models that include the plasma pressure and the gravity. Those models have been computed by Cohen et al., and there are configurations actually where we can see loops that interconnect the star and the planet. So those loops are predicted also by the numerical model configuration like this. And in those loops, you can see field lines that are strongly stressed. So even in those models, you can expect that a large amount of energy taken from the orbital motion is stored into the magnetic field. For distant planets, you may also predict the magnetic field with magnetized stellar wind models, like those computed by Aline Vidotto and her team. Those models can be based on Zeeman Doppler imaging, giving you the large-scale stellar field applied as a boundary condition at the base of the model. And then you extrapolate the potential field up to some distance, and then the field is open by the flow of the wind into almost radial configuration. So I come to my conclusion. I have presented a few clues of star-planet magnetic interaction, focusing on the case of HD 179-949. In that case, we see a chromospheric hotspot and possibly also some coronal signal that are in phase with the orbit of the planet rather than with the stellar rotation. We know a few other systems that show similar phenomenology. And the interesting point is that if we can identify the mechanism responsible for the phenomenon, we have an opportunity to estimate the energy involved and also estimate the field of the planet, at least for some class of models. I have briefly introduced the three classes of models: the Alfven wing, the unipolar inductor, and analytic models based on force-free approximations. Among those models, only the interconnecting loop model seems capable of accounting for the power in the observed chromospheric emission, that is of the order of 10 to the 20, 10 to the 21 watts. The unipolar induction model proposed by Lane and Lin provides a power that is comparable, but it has stringent requirements and depends on poorly known quantities, like the resistance, the electric resistance in the stellar atmosphere, that is also a function of the penetration depth of the electric currents, or if you want, of the Alfven waves, because they are alternate currents that are induced by the motion of the planet in the stellar field. Particularly interesting is the case of radio emission from Proxima Centauri, and this emission actually is a power level of the order of 10 to the 14 watt. So even if the planet is quite far from the star, the distance is of the order of 70 stellar radii, because the star is actually very small. It's a late M dwarf, much smaller in radius than the sun. In that case, the lower level of power can actually be explained by the magnetic reconnection model. So you don't need an interconnecting loop, but you can deliver the amount of power you need by the interaction between the field of the stellar wind and the field of the planet, assuming that the planet has a field of the order of at least 1 Gauss, which is reasonable for a planet of 1 Earth mass, similar with a dynamo similar to that of our Earth. The interesting point is the greater sensitivity of the radio detections in comparison to the detection that we can make with chromospheric hotspots. So I think that radio observations are the best way to pursue the detection of magnetic star-planet interaction, also because the electron cyclotron maser mechanism is capable to, produce an efficient conversion of magnetic energy into radiation, much more efficient than the simple chromospheric heating we expect in the case of the chromospheric emission. Thank you very much for your attention and your patience, and I stop here.
Thanks a lot, Mucho, for this very interesting talk. Pedro and I already the two persons that invited Mucho, who very rapidly accepted our invitation. And it's really a pleasure. He's really a big expert. He actually, if you have an idea, he can convert this into a model. So it's really creative. It has been very useful. So it's really an honor to have him with us. I'm sure there will be questions. So please.
I have one.
Okay,
So I don't want to start. I mean, if someone else in the.
No, it's okay.
I have two questions, but I can do one and then you can do yours. And then I have one question about the endors that you were showing. All of those ones are mid to late endors, right? I understand that you haven't been able to find that planet for GJ 1151, but I was thinking, is this the fact that you can get this signal, is it something about being kind of in the peak of the initial mass function, right? Most of the endors are going to be around M3 and 4 and 5, right? Where these stars are. Or is it something about the magnetic fields, right? Where they become fluid convective and we may not understand very well, like how, magnetic fields are formed from the star. Like, do you think that this is something that has to do, that it is specific for this type of stars, like mid to late M's, or why these stars?
Well, this is a very interesting question. Actually, we can try to answer from the observational point of view. There are programs with LOFAR and other radio instruments dedicated to detect this kind of coherent emission, and certainly Miguel can tell you much more than me because I'm not an expert in that. So first I would say it's better to increase the observational sample, and there are indications that several other stars observed with LOFAR, other M dwarfs more or less similar to GJ 1151, show episodic coherent emission. Why we observe this in that star? Well, it could be that those stars have a relatively strong field in comparison to earlier type stars. Relatively stronger means that the field in the photosphere is of the order of hundreds of Gauss, even if the star is rotating slowly. Proxima has a rotation period that is of the order of 80 days. But since convective motions are very slow in those stars, and they, as you said, are actually developing over most of the volume of the star, then you have a powerful dynamo action, because from the observations, we know that the critical parameter to produce a strong magnetic activity is actually the Rossby number, the ratio between the rotation period to the convective turnover time at the base of the envelope or in the middle of the envelope if the star is a very deep convection zone. In those stars, the Rossby number is small, is less than 1, and in many cases even less than 0.1, which means it is so low that we expect star spots with the fields, localized fields of the order even of tens of kilogauss, and the global field that can be easily of the order of hundreds, several hundreds of Gauss. In stars more similar to the Sun, the field is lower, especially the global scale field is of the order of 1 Gauss in the Sun, of the order of 10 Gauss in those F-type stars like HD 179, 949. So M-type stars give us a more favorable environment from the magnetic point of view, as far as we understand. So let's see what happens in the near future. I think there will be many promising new results that are coming, actually.
Yeah. If I may add, that was part of my question, that what is maybe the best to you, not Mucho, best instrument, best wavelength range, radio, and or this ultraviolet or optical to find signature. So as Lucio showed, for this F-type star, maybe this chromosphere, looking for chromosphere spots is more promising because the magnetic field is so low that in the radio we are really having difficult chances are null. Instead, on the other, N dwarf star, late type stars, close to fully convective, then magnetic fields are so large that this gives us a very good chance.
Yeah, I was thinking exactly that, basically, I mean, there is that difference, right, between the early M's and the late M's, and it's that they are fully connected. So those, my question was like, those are the ones that we should target, or should we try to get some M zeros and ones and see what we can get?
Okay.
Within the M's, not other.
Well, I'm not an expert on the radio side, so probably Miguel, correct me if I'm wrong. Probably it depends on the instrument that you have, in particular the band that you can observe, because this electron cyclotron maser mechanism has a dependence of the field. You have that the peak frequency is proportional to the field. So if you want to observe at 1.6 gigahertz, then you need fields of the order of hundreds of Gauss, which means M-type stars, actually. And what is more important is probably the Rossby number, because we don't see a clear change in the magnetic activity level or in magnetic activity indicator when we move from M stars that are partially convective to those that are completely convective. So probably the dynamo in a deep convection zone and the dynamo in a fully convective star are working more or less similarly. Okay. There are people saying that there can be changes in the geometry of the wind, for instance. But when we go and measure the intensity of the field in the photosphere, I think there are not really large difference between the two kind of stars with different internal structures. So from our point of view, probably the best parameter is the Rossby number.
Please.
Just wanted to add that there is actually a difference which might be interesting. I mean, as you go to fully convective stars, we tend to find significantly, on average, significantly more stars with simple magnetic field geometries. The fields are strong, right? Both for partial and fully convective stars, but in fully convective stars, we find stars with more like dipole-like geometry, which favor probably or make it easier to study these mechanisms, because the field is the polar field in this case of the star is significantly stronger than in partial convective. That might be a difference.
Yes, thanks for that point, because you are right. Actually, it's the large scale field which is important. So if the field is mainly in the dipolar mode, that can help a lot in comparison to multipolar fields.
Yeah, that's right. Thanks a lot for this. Ben, you wanted to ask something?
You want to go? No.
No, I can ask later.
I can ask later too, because I really.
Good.
Mitchell, you were mentioning how difficult it is to get observing time to try to confirm any of these interesting candidates. We tried with GJ 1151. We went to Maroon X Gemini. We didn't get the time to try to find this possibly very small planet that is causing this radio emission, supposedly to be a proxy for star-planet interaction. So, and these are very small, very small periods, very short periods. We don't need that much time. Now, when we translate all this into trying to see what is the role of the magnetic cycle of the star, these stars have magnetic cycle, like in the sun, the 11-year magnetic cycle in the sun. then we need observing programs of many years to cope with some of the phases of these long-term cycles. Well, my question to you is, would it be possible to model the effect of the change in the magnetic cycle of the star, of magnetic field of the star in this magnetic cycle, the effect on the switching on and off of the star-planet interaction, because we see that in some phases of this cycle we seem to be detecting this star-planet interaction, but in other phases we don't. What do you think about this possibility of?
Well, this is actually a very important point. Antoine Strugarek has tried to address that point using numerical simulations, but actually numerical simulations do not produce the interconnecting loop geometry, because probably you need a very efficient way to dissipate energy to keep the connection. As I told, the field must be kept close to potential, which is really difficult in a numerical simulation, because in a real loop you may have a dissipation on very small scales, and so that becomes very efficient. In numerical simulations, you are limited actually by the resolution of your grid. So actually, I expect to have changes in the stellar field, as you said, along the cycle. Probably when we look at the sun and assume the sun as a paradigm, the best phase to have is similar to a potential field is when the sun is actually at the minimum, in some sense, of the activity cycle, because that is the moment when the field has a global geometry more or less similar to a dipole. When you go to the active sun, you have lots of active regions on the sun, especially close to the maximum, and then the field is dominated by the spots. Spots are small, yes, but they are much stronger than the global polar field of the sun, so they impact on the large scale field is significant. So yes, actually this is something that we can try to do in the future, maybe looking at the sun. Some people already attempted that, in particular Kramer used the sun, the solar magnetograms to try to predict the star-planet interaction in some in systems like HD 1799549. So yes, it's an approach that we need to extend.
Thanks. Well, Barbara?
Yeah. Okay, I'm gonna move on from my words, but I was thinking about this. I think it's fantastic if we could measure magnetic fields of exoplanets. I think that's fantastic. You show a slide where it's a Taboo and the three other ones, right? And with according to the model of the magnetic fields estimated for the planet, right? How likely it is that those planets can create that magnetic field, being so close? I don't know if there are tidal effects and things like that.
Yes, that's an important point, I think. Well, first you need a dynamo. And the dynamo is a threshold process in the sense that if the body is rotating too slowly, then you have no way to amplify the field. The field, if it is present, simply goes away. It decays, and there is no possibility to keep a stable field. But if the planet is rotating fast enough, and fast enough means with a rotation period that is at least comparable with that of the convective turnover time at some depth in the internal convection zone, then it's possible to have a dynamo. And once the dynamo starts, the limit of the field depends on the nonlinear process that sets it, in the sense that we have a theory of linear dynamos in which we prescribe the velocity field and we compute the field geometry. But the field intensity cannot be estimated with those linear models. We have an idea about the field intensity if we can prescribe a mechanism that limit the field in the nonlinear regime. Here, in this model by Yadav and Thorngren, they assumed that the field basically is limited by the kinetic energy density in convective motions. And that energy is boosted by the fact that 1 or 2% of the stellar irradiation is captured by the planetary atmosphere, and instead of being immediately re-irradiated, it is reprocessed in the interior. So it goes into the interior because there is, for instance, a strong meridional circulation, bringing hot material from the surface to the interior. And this produces an inflation of the planet, but also it gives more energy to the convective motions. And they assumed that this energy is used to boost the dynamo. So a planet more or less similar to Jupiter, in this case, can have a field that is up to 10 times stronger. But you need this trick in some sense.
Thanks. Questions? I had a question about, so this interconnecting loop model provides enough power to explain this chronospheric pulse. If you could show again this result by Skolnick and Yam, I have a. And then,
you mean this one?
Yes, apparently this is not this one. The observations.
Okay. The observations.
No,
okay. The table.
I think was one of the initial.
I have a table with the observed power, the power based on those observations.
Actually, in the previous plot, I think is
this one.
So of course, this relies on the fact that these signals are real and are attached to the
planet interaction.
Right?
Yes, this is the main hypothesis that we do.
Because I think in that one they look more clear, but I was a bit mistaken by the previous plot where actually I think they repeated the same in the phase. They repeated
yes. Actually, this you are right. This is actually
right.
repeating in two times the same.
Yeah, which I think this is really a trick, but
Yes.
You get the impression, oh wow, it's so clear that it's periodic, but then.
No. You are right. You are right.
The other one, the other ones look more convincing.
Yes. I took the plot from the review by Skolnick and Lama in the Handbook of Exoplanets, and of course they are strongly in favor of the existence of this kind of interaction. But there is a small false alarm probability. We can also discuss what is the meaning of small. In this case, it's of the order of 1–2%. The false alarm probability is not small in the sense that it's 10 to the -4, 10 to the -3. It's something close to 1%. So we are discussing about an effect that is just at the limit of the present detection. And the problem is that we know that the effect is not stationary. And when you submit your application to the time allocation committee, they say, well, you are not sure to observe it. So why give you time? It's a big problem, actually. You cannot make progress without more observations, but you cannot get time to make observations that necessitate of a very strong time investment of medium size or big telescopes without certainty that you observe something. Yes, that's a big problem. I think.
Okay.
I'm a complete ignorant on this field because I come from extragalactic. So maybe what I'm going to ask is nonsense. But I've understood that you're talking always about isolated stars, right?
Yes, these are not close binaries. A star with its planet. The planet is close to the star in the sense that the distance of the planet from the star is within 0.1 astronomical unit. So we have no such kind of planet in the solar system, but they are common because selection effects favorite the discovery of this kind of star-planet system. So we know hundreds of hot Jupiters. At the moment, there are more than 300 hot Jupiter systems, actually.
I guess the binary stars complicates everything a lot, so.
Yes, if it's a close binary, yes, you are right. I mean, a binary with a period of a few days is a system where it is really difficult to detect the planets. Sometimes you can observe planetary transits by a planet that is, orbiting around the couple, around the close binary stars. These are actually observed by Kepler. We know a few tenths of those systems, but only because they are transiting. Otherwise, the stars are so active that you cannot measure the wobble of the system of the double star due to the planet, because the stars are very, very active in that case by their own. They have strong fields, and that makes very, very uncertain the measurement of the radial velocity. So actually, we are strongly limited by selection effect.
Thank you for the nice talk. I know that you are very much involved in capital vision, but I have two questions. One is, you have a prospect of synergy between Plato. How this would be with Plato? This kind of studies. And the other one is, what about photometric magnetic indices? Do you think it would be possible to use photometric magnetic indices for that study?
Yes, Plato will help us a lot, I think. First, by detecting more hot Jupiters around bright stars. Bright stars are the best candidates also to look for those chromospheric hot spots. We may also have some effect visible in the optical. There have been proposals about that. Very recently, there was a paper by Castro Gonzalez and collaborator by the Porto group that used the TESS satellite, and they claim to have found a signal in a system with an eccentric planet. The planet again is very close by to the star. It's just, I think, 6 days of orbital period, and they see that there is a signal at the orbital period in the periodogram. They don't see a signal related to stellar rotation, and actually they gave arguments suggesting that the star is rotating with a completely different period. So they are pretty confident that this signal in the optical is due to the planet. It could be a sort of flaring that is preferentially occurring close to the periastron. But actually, it's very, very difficult to understand. It would be better to have a confirmation from another passband, like X-rays, ultraviolet, or maybe to observe a chromospheric hot spot. But that requires dedicated observations, of course, which is not easy to get. But yes, we should expect to observe something, even if it's not completely clear what can produce a signal in the photosphere, because you need even larger powers by, well, 10 to the 20 is just the minimum, 10 to the 20 watts to produce something at the millimag level in the photosphere. Probably you need 1 order of magnitude more. So that is also an open point. What could be the mechanism in that case? Tidal stimulation of magnetic field emergence that produce flaring or active regions, or is the same mechanism just working with, may say, a strong planetary field? I don't know, but we should be prepared to that actually, and Plato can help us.
Just before Jose Luis now, I'm noticing that the two lower panels are also repeating this. So it's only the one that in the top that, the blue line that shows some signal that apparently is true, but the other ones is kind of repeating the same dots in two phases, right?
Yeah, yes. It's always in two phases because the thing.
More carefully at this paper.
Yes.
Okay, so
Well, the motivation for repeating goes back for us. I mean, Pedro may probably also comment on that, to the old times when we do photometry from the Earth, photometry of late type active stars from the Earth. Since the phase coverage was very, very uneven, we used to repeat or extend at least the phase behind 0-1 in order to better see the population.
maybe I should have done the same trick for our
Yes,
paper.
yes. So for me, this is
complete detection.
Yes. So look at the
Yeah.
x-axis. That's important. This is the important message. Look at the x-axis.
Jose Luis.
There was a question on photometric indices. Maybe can you comment on that, and then I make my question.
Yes.
Photometric indices, when you observe using data from a space telescope, usually you have flux in only one passband because that is done to optimize transit detection. So all the photometric indexes should be based only on one band. We don't have, usually we don't have color. Maybe Corot was the only mission that gave us some color information. But then Kepler, TESS, and Plato will not give us color information. In Plato, there are actually two fast cameras that will give us a blue and red band flux, but is for really very bright star, magnitude at most 8. The limit is 8.
Okay, but would photometric indices be feasible from the ground with specific?
Can you put the calcium 2H and calcium line and the
Okay, this one. Okay.
Yeah, we try to investigate if it was possible to observe from the ground because it is so expensive to use high resolution spectrographs. We decided to look into this problem if photometry could help us detect the star-planet interaction in the chromosphere in these straight lines. But you see the variation is just in the core of the line, and there are no narrow enough filters that can provide us the precision that is needed to detect these very small signals. All the filters that we could find are very close, and we couldn't find any.
Yeah, but you can build one, but it's not available.
Yeah, you could build one that is narrow enough, but then again, the variability of the line in general. This maybe is a possible way to be explored, but it's gonna take a lot of effort. In our case, it was not worth it. Just more.
You can.
And my own
And then do
question,
your own question.
in analogy with the solar system, Jupiter Io system, we know that Io has a plasma torus of sodium, which provides plasma. Is there anything like that that could have an effect on extrasolar planets? I mean, release of atmospheric plasma from
Yes, thanks for the question. I have my personal opinion about that. Actually, observations of lines like the helium-1 at 183 nanometers in the near infrared have provided evidence for some cases where you have an extended tail of evaporation from the planet. In some cases, so extended that you are actually encircling all the orbit of the planet. That may have an impact, in my opinion, on the large-scale geometry of the magnetic field, because if the stellar wind is not yet accelerated enough, because we are really close to the star, that torus of ionized matter can keep the stellar field lines closed, which is a configuration different from that in the solar wind. In the sun, after about 2.53 solar radii, the field opens. But maybe in some of those stars with a strongly evaporating hot Jupiter, you may have some configuration with the stellar field lines that are mainly closed in the equatorial plane. Maybe it's not stable. A strong stellar flare can destroy that configuration and blow away the torus. But it's a fact that observations seem to indicate that, at least in some cases, evaporating hot Jupiters are producing a circumstellar torus of plasma around their stars.
Thank you very much for the answer. More answer questions? There are more questions? Line? Yeah, online.
No questions here.
I think it's now it's 2 p.m. And so let's thank again Mucho Lanza for the very He will be around this afternoon, but